Hello and welcome to Math Zone African Motives. In this tutorial, we will be diving into some advanced integration techniques. Specifically, we will explore the method of substitution, but with a focus on integrals where the substitution is not immediately obvious. By the end of this video, you will be able to perform these other substitutions to solve complex integrals, including those involving roots, powers of linear factors, and trigonometric expressions. The core idea is to transform the integrand into a simpler form that we can integrate using standard rules. Let's get started with our first set of examples. We'll begin with the first two examples from our worksheet, which both involve the square root of a linear expression. Our first problem is the integral of x times the square root of x minus 1. Our objective is to find the antiderivative of this function. The key here is to notice the square root of x minus 1. This suggests a substitution that will eliminate the square root. Let's use the substitution u equals the square root of x minus 1. Squaring both sides gives us u squared equals x minus 1. This is a common strategy when dealing with square roots. Now we need to find dx in terms of do. We can differentiate the expression u squared equals x minus 1 implicitly with respect to x. The derivative of u squared with respect to x is 2u do over dx. The derivative of x minus 1 is simply 1. Rearranging this, we find that dx is equal to 2u do. This is our substitution for dx. Great, we have everything we need to rewrite the integral in terms of u. We have x, we have the square root term, and we have dx. Substituting these into our integral, we get the integral of u squared plus 1 times u times 2u du. See how everything is now in terms of our new variable u? Now we can simplify and integrate. Let's start by multiplying. The u and the 2u multiply to give 2u squared. We can pull the 2 out of the integral and then distribute the u squared into the parenthesis. This gives us the integral of u to the 4th plus u squared. This is a standard polynomial that is much easier to integrate. Using the power rule for integration, the integral of u to the 4th is u to the 5th over 5, and the integral of u squared is u cubed over 3. Don't forget the constant of integration, c. Distributing the 2 gives us our answer in terms of u. But remember, we need our final answer in terms of the original variable, x. So, our last step is to substitute back. We replace every u with the square root of x minus 1. This gives us the final answer. We can also write the square root as an exponent to simplify the expression further. Comparing our result with the memo, we can verify that our answer is correct. Verified. Now let's tackle a similar problem, but with a slight twist to solidify your understanding. This time we have the integral of x squared times the square root of x minus 1. The main difference is the x squared term. Fortunately, we can use the exact same substitution as before. It is still the best way to handle that square root. We'll let u equal the square root of x minus 1, which means x equals u squared plus 1 and dx equals 2u du. These are the building blocks for our transformation. The only new piece we need is a substitution for x squared. Since we know x equals u squared plus 1, we can simply square that expression. So x squared becomes the quantity u squared plus 1 squared. Expanding this using the binomial formula gives us u to the 4th plus 2u squared plus 1. Now we are fully equipped for the substitution. Substituting everything into the integral, we get the integral of our new expression for x squared, times our u for the square root, times 2u for dx. Once again, the entire integral is now in terms of u. Let's simplify this just like before. Multiply the u and 2u outside the parenthesis to get 2u squared. Then distribute the 2u squared to every term inside the parenthesis. This results in the integral of 2u to the 6th plus 4u to the 4th plus 2u squared. This is another straightforward polynomial to integrate. Applying the power rule to each term, we get 2 times u to the 7th over 7, plus 4 times u to the 5th over 5, plus 2 times u cubed over 3, all plus c. And of course, for our final answer, we must substitute back u equals the square root of x minus 1. Replacing u with the square root of x minus 1, we get our final expression in x. A quick check against the provided solution confirms our work. Verified. Let's move on to our third example, which introduces a new situation. The degree of the numerator is the same as the degree of the denominator. The problem is the integral of x over x plus 1. Notice that the degree or highest power of the numerator is 1, and the degree of the denominator is also 1. The general rule to remember is this. When the degree of the numerator is equal to or higher than the degree of the denominator, our first step should be polynomial long division. This simplifies the fraction into a form we can easily integrate. So let's divide x by x plus 1. We ask, what do we multiply x by to get x? The answer is 1. We write 1 above the x. Then we multiply 1 by the entire divisor x plus 1 to get x plus 1. We subtract this from the numerator. The x's cancel, and we are left with negative 1. This is our remainder. We can now rewrite the fraction x over x plus 1 as the quotient plus the remainder over the divisor. So x over x plus 1 equals 1 minus 1 over x plus 1. This looks much friendlier to integrate. Our integral becomes the integral of the quantity 1 minus 1 over x plus 1 with respect to x. We can integrate this term by term. The integral of 1 is just x. The integral of 1 over x plus 1 is the natural logarithm of the absolute value of x plus 1. So our final answer is x minus the natural log of the absolute value of x plus 1 plus our constant c. This method of long division is a powerful tool to simplify rational functions before integration. We have successfully found the antiderivative. Verified. Now let's explore an alternative way to solve that last integral. The method of substitution. We're going to solve the integral of x over x plus 1 using a different strategy. In this case, a natural substitution is the denominator. Let's set it equal to x plus 1. Differentiating both sides gives us du equals dx. So our dx substitution is very simple. We also need to express the numerator, x, in terms of u. From our substitution, x equals u minus 1. Now let's perform the substitution, replacing x with u minus 1 and x plus 1 with u. The integral becomes the integral of the quantity u minus 1, all over u, with respect to u. Notice that just like in the long division method, we've replaced a complex integrand with a much simpler one. To integrate this, we can split the fraction. The integral of u over u minus 1 over u is just the integral of 1 minus 1 over u. This is exactly the same form we got from long division. This shows how different approaches can lead to the same result. Let's integrate this with respect to u. The integral is u minus the natural logarithm of the absolute value of u plus c. Our final step is to substitute back x plus 1 for u. This gives us x plus 1 minus the natural logarithm of the absolute value of x plus 1 plus c. Looking closely at this expression, we have a constant 1 inside the c. Since c represents an arbitrary constant, we can absorb the 1 into c. The quantity 1 plus c is just another constant, which we can still call c. This is why our final answer is x minus the natural logarithm of x plus 1 plus c. Verified again, and this demonstrates that substitution can be a valid alternative to long division in these cases. Let's move on to the fourth example, which combines both roots and the need for long division. The problem is the integral of the square root of x over the square root of x plus 1. Our objective is to evaluate this integral. As always, the first thing to do is simplify the root. A good substitution here is u equals the square root of x. If u equals the square root of x, then x equals u squared. Differentiating gives us dx equals 2u du. Now we substitute these into our integral. This gives us the integral of u over u plus 1, all multiplied by 2u du. Simplifying this, we get the integral of 2u squared over u plus 1. Notice the structure of our new integral. The degree of the numerator 2u squared is 2. The degree of the denominator u plus 1 is 1. Since the numerator's degree is higher, we must use long division. Let's divide 2u squared by u plus 1. What do we multiply u by to get 2u squared? That's 2u. We write 2u above the u. Multiplying 2u by u plus 1 gives 2u squared plus 2u. Subtracting this leaves us with negative 2u. Then we bring down the next term, which isn't there, so we write ta to 2u. Now we ask, what do we multiply u by to get ta to 2u? The answer is 2. Multiplying 2 by u plus 1 gives 2u minus 2. Subtracting this leaves a remainder of 2. So 2u squared over u plus 1 is equal to the quotient, 2u minus 2, plus the remainder, 2, over the divisor, u plus 1. Our integral now becomes 2 times the integral of this simplified expression. We can now integrate term by term. The integral of 2u is u squared. The integral of 2 is 2u. The integral of 2 over u plus 1 is 2 times the natural log of the absolute value of u plus 1, and of course the constant c. Finally, we substitute u equals the square root of x back into our result. This gives us the square root of x squared, which is just x, minus 2 times the square root of x, plus 2 times the natural log of the quantity square root of x plus 1 plus c. Verified. Let's tackle the fifth example, which is very similar to the last, but serves as good practice. We need to find the integral of 1 over the square root of x plus 1. Notice the root in the denominator. Just as before, this suggests the substitution u equals the square root of x. So we have u equals the square root of x, which means dx equals 2u do. We substitute these into our integral. The integral becomes the integral of 1 over u plus 1 times 2u do. This simplifies to the integral of 2u over u plus 1. Again, the degree of the numerator is 1 and the degree of the denominator is 1. They are equal, which means we should use long division. Dividing 2u by u plus 1, we get a quotient of 2 and a remainder of 2. Therefore, 2u over u plus 1 can be rewritten as 2 minus 2 over u plus 1. Now our integral is much simpler to evaluate. We integrate term by term. The integral of 2 is 2u, and the integral of negative 2 over u plus 1 is negative 2 times the natural log of the absolute value of u plus 1 plus c. The final step, as always, is to substitute back for x. We replace u with the square root of x, giving us our final answer of 2 times the square root of x, minus 2 times the natural log of the square root of x plus 1 all plus c, verified. For our sixth example, let's look at an integral that is a perfect candidate for standard substitution to help us recognize these cases. The problem is the integral of the square root of x times the quantity x times the square root of x plus 1 raised to the 5th power. Our goal is to solve this integral. Here, we use a simple u substitution. The key is to look for a function and its derivative. The derivative of the term in the parenthesis is related to the square root of x outside. Let's make the substitution u equals x times the square root of x plus 1. This is equivalent to x to the 3/2 plus 1. This entire term will simplify our integral. Now we find do by differentiating u with respect to x. Using the power rule, do over dx equals 3/2 times the square root of x. Rearranging this, we get dx equals 2 over 3 times 1 over the square root of x times du. Look closely at the derivative. Notice the square root of x from the derivative in the denominator. This is perfect because we have a square root of x in the numerator of our original integral. Let's substitute. The integral becomes the integral of the square root of x times u to the 5th times our substitution for dx. As you can see, the square root of x in the numerator and the square root of x in the denominator cancel out. We are left with a very simple integral, 2/3 times the integral of u to the 5th. This is the goal of a good substitution. We've simplified a complex problem into a basic one. Integrating using the power rule gives us 2/3 times u to the 6th over 6. This simplifies to u to the 6th over 9. Finally, we substitute back our expression for u. The final answer is the quantity x times the square root of x plus 1, all raised to the 6th power, divided by 9, plus c. Verified using memo. Our 7th example is marked as enrichment, and it is indeed a bit more challenging. The problem is the integral of 1 over the square root of the quantity square root of x plus 1. Notice the nested square root. To simplify this, the most effective strategy is to try and eliminate the outermost root. This means we should substitute for the entire expression inside it. Let's make the substitution u equals the square root of x plus 1. The goal is to isolate dx in terms of u and du. Squaring both sides will remove the main square root. So u squared equals the square root of x plus 1. Now we need to isolate x to find its derivative. Squaring again gives u to the fourth equals x plus 1. So x equals u to the fourth minus 1. Now we can easily find dx by differentiating this expression with respect to u. The derivative dx is simply 4u cubed du. This is our full substitution kit. We replace the denominator with u and dx with 4u cubed du. Substituting these into the integral, we get the integral of 1 over u times 4u cubed du. This simplifies dramatically to the integral of 4u squared du. This is a testament to the power of a strategic substitution. Integrating this is straightforward. The integral of 4u squared is 4 times u cubed over 3 plus c. Our last step is to substitute back our original expression for u. Substituting x plus 1, for u, we get our final answer. Notice how clean it is despite the complexity of the original problem. Verified. Now let's revisit 2 examples from the beginning of our session, using the methods we've learned. First, the integral of x plus 1 over the quantity x minus 3 squared. We already know this can be done with substitution. The note here suggests another method, partial fractions, which we'll cover in a later unit. For today, let's solve it with a standard u substitution. Let's set u equal to the base of the power in the denominator, x minus 3. Differentiating gives us du equals dhi. We also need to express the numerator, x plus 1, in terms of u. From our substitution, x equals u plus 3, so x plus 1 equals u plus 4. Now we substitute all of this into the integral. We get the integral of u plus 4 over u squared du. This is a degree 1 numerator over a degree 2 denominator, so we don't need long division here. We can just split the fraction. This becomes the integral of u over u squared plus 4 over u squared. Simplifying the terms, we get the integral of 1 over u plus 4u to the negative 2. This is a very easy integral to solve. The integral of 1 over u is the natural log of the absolute value of u. The integral of 4u to the negative 2 is 4u to the negative 1 over negative, which simplifies to negative 4 over u. Plus c. Our final step is to substitute back x minus 3 for u. The result is the natural log of the absolute value of x minus 3 minus 4 over x minus 3 plus c. Verified. This is a great example of how simple substitution can be incredibly effective. For our 9th and final example, we will revisit a product of 2 polynomials, each raised to a power. The problem is the integral of the quantity x minus 2 squared times the quantity x minus 3 cubed. Our task is to find the antiderivative. The key to simplifying an integral involving multiple factors, especially when they differ by a small constant, is to choose a substitution based on one of the factors. In this case, let's choose u to be the factor x minus 3. Differentiating gives du equals dx. This is a great simplification already. Now we need to express the other factor, x minus 2, in terms of u. From our substitution, we know x equals u plus 3. So x minus 2 equals u plus 3 minus 2, which simplifies to u plus 1. Thus, x minus 2 becomes u plus 1. Now we can rewrite the integral entirely in terms of u. We replace x minus 2 with u plus 1 and x minus 3 with u. This gives us the integral of u plus 1 squared times u cubed duco. This transformed integral is much easier to manage. Let's start by expanding the term u plus 1 squared. Expanding the binomial gives u squared plus 2u plus 1. We then multiply the entire expression by u cubed. This distributes to give u to the 5th plus 2u to the 4th plus u cubed. We now have a standard polynomial integral. Using the power rule for integration, this becomes u to the 6th over 6 plus 2 times u to the 5th over 5 plus u to the 4th over 4, all plus c. For our final answer, we must substitute x minus 3 back in for u. This gives us our final antiderivative in terms of x. The key was a clever substitution that turned a complicated product into a simple polynomial. Verified. Let's quickly recap what we've learned today. We focused on other substitutions that aren't immediately obvious. You've now seen strategies for dealing with integrals involving roots, like substituting for the entire root or the nested part of a root. You've also seen how to simplify integrals of rational functions by using polynomial long division, when the degree of the numerator is equal to or greater than the denominator. Finally, we practiced making strategic substitutions to turn products into simpler polynomials. Remember, the goal of any substitution is to transform a complex integral into a simpler one that can be integrated using standard rules. It's like finding a hidden path through a maze. Thank you for joining me on Math Zone African Motives. I hope this tutorial has been helpful. Don't forget to like this video, leave a comment if you have questions, and be sure to subscribe for more tutorials like this one. Until next time.